Okay, yesterday we were doing angular momentum and its conservation. But those questions were directly related to a rigid body, and something about that rigid body had changed. So if we use just the 2 or 3 examples from yesterday, we had a spinning merry-go-round where the kids walked to the center. So in this particular example, there was no external torque. I keep using this word, but in your notes or how you explain this, there was nothing outside of the system that was acting on the system itself. So a kid wasn't dragging a foot off the edge, or the ice skater wasn't hitting her toe against the ice, her other toe against the ice. We were talking about there was nothing external to the system that was causing a torque on the system. In that instance, we were saying that the initial angular momentum was equal to the final angular momentum. And in that discussion, we tried to make a very clear distinction that our system was made up of many component parts, but a change in where they were located on the object affected the moment of inertia of the system. So the kids walked towards the center, they made the moment of inertia of the system smaller. In order to maintain momentum, the system had to speed up. Now, what's different about this conversation than other conversations we've had other conversations where momentum has been conserved, where a single car strikes another car. In every one of those collisions, we usually dealt with objects that were separated and interacted for a brief moment. And during that brief moment, momentum was exchanged, but almost every single time, energy was lost during those collisions. Here, we have a condition where the energy of the system after the collision was greater than the energy before. So it's important to recognize that in this unique circumstance, I'm trying to be very careful here, this is the only circumstance where this tends to happen. The kids were able to add energy to the system, but couldn't affect the momentum. So how I'd like you to kind of put this in your notes, or how I think you should put this in your notes, is to understand if there's no external torque, you can't change momentum. You have to touch something outside the system to change the momentum of the system. But you can change the energy of the system. So in this circumstance, those kids walking towards the center added energy to the system. We don't have a similar example in linear mechanics. If a kid is running on the street and they run faster, their momentum changes. Momentum's not conserved. There was an external force of friction acting on the kid. If a rocket ship is in space and it fires its engine, now it's a little bit different. The one rocket ship can go faster, but it expelled gas that stayed in place or went backwards. So we still had two things that separated. The momentum of the system is the same. Does that increase the energy? That's likely. That's a similar circumstance. Or a spring that's maybe between two cars. If they're just sitting there on the track, what's the momentum of the system before? 0. I initiate the spring, the cars separate. The momentum of the system after, still 0. But now the system had energy. It didn't have energy before. Those are good circumstances that are like this, where the energy of the system changed due to the action of the objects without affecting the momentum of the system. So again, the best analogy to this is to consider that track, where the before case has the cars sitting together with a spring between them. I don't know why I wrote them on the side like that. And then the secondary case is, the cars are separating. The momentum is still conserved. The MV before is equal to the MV after, mostly because it was 0 before. But afterwards, there's clearly kinetic energy here when there was no kinetic energy before. This is a similar circumstance. Now, why I want you guys to get on that spinning thing and pull your arms in while holding the books, it's so you can feel that you really have to work against those books in order to make a difference in how fast you're spinning. Now, today we're going to talk about a different circumstance, something completely different. And to kind of start us off, I want to put a kind of a baseline in here. And I want to start this example with two pucks. So let's say that these two pucks have equal mass and currently have equal velocity. And they're traveling towards each other. And I'm going to say that they are made of something that's sticky like Velcro, so that when they make it to the center, they will stick together. If I'm careful and I make sure that they're both fired evenly on this surface, the momentum both before they strike each other and after they strike each other will be zero. And in this collision, I think we can all agree, if they meet there in the center, they're likely to stick together and stop. Does that make sense? So this fits with our expectation, where we talk about momentum before and after equal to zero, and how during this collision, the force on both cars will be equal and opposite, will stop both cars. What happens if, instead, we start that car there, not car, but you get what I'm saying. If we start this disc here, and hold on just a minute. We start that disc here. So, there. Still made out of a sticky substance. They still are going to meet in the middle. But when they meet in the middle, are they going to stop? It's a more complicated idea, right? Because if they meet in the middle, their center of mass will still be stuck here in the middle. It won't be moving, but are they going to be stopped now? What's the likely outcome of this collision? Got one idea, and only one person has an idea. Go ahead. Slow them down? I think it'll be different than that. I think it'll be different than slowing them down. It may, I don't really know. But will there be motion after this collision? Yes, sir? I think that's what's going to happen. I think they'll make it there to the center, and they will begin to spin in a circle. You've seen this. Two ice skaters meet in the center of the ice and grab each other's hands and spin. This is a similar kind of circumstance, wouldn't it? They touch at the edges, they'll start to spin around the outside of each other. Yeah?
The surface area doesn't affect the friction, right? Like the amount of area that they're touching.
No, we just assume that they stick together enough. So now, in this example, there is clearly angular momentum after the collision. But there's no external torque present before the collision. Now, I'm saying this because what this suggests is that the system had to have angular momentum before the collision. And so there is a way to measure the angular momentum of a point particle that is moving through space. And that's what I want to talk about today is where was this guy's angular momentum before the collision? So let's put him back here. Get rid of this stuff for a minute. And let's discuss the way we describe an object's angular momentum. Now, we're talking specifically today about angular momentum for a point mass. Now, this object isn't a point mass, but we treat it like a point mass for this circumstance. Before I go into all of the details, I want to remind you of something that it seems so ridiculously subtle, but it's important that you at least have it in the back of your mind. Whenever we have done an example or a lab, we've been able to observe velocity because we were in a reference frame that was not moving with respect to the object, right? The car on the track. if I put the motion sensor out there, the track and the motion sensor were not moving with respect to themselves, right? The motion sensor just sat there, right? The car moved in front of the motion sensor. We assumed the track and the car were moving with respect to each other. But we could measure that because we had a motion sensor that was stuck on the track. So that allowed us to have a point of reference that we said wasn't moving. If you're standing on a street corner, cars are passing you by, you assume that you aren't traveling towards the car. You assume that you are stopped and at rest with respect to the ground, and the car is traveling towards you. Does that make perfect sense so far? I mean, you have to understand that what's about to happen here is going to change that perspective. If you're in space with no points of reference and something passes you, how do you know whether you're moving or the other object is moving? This is what we mean by a reference frame. We provide reference so that motion can be measured, but if you don't have points of reference, that makes it more difficult. Angular momentum, specifically angular momentum, picks a specific point in space to be a point of reference for this measurement. I'm going to say that like once more, because if you could write that down, it will make a massive difference, because we didn't need this for linear momentum. For linear momentum, the entire space was our reference frame, because we assumed we weren't moving. The object was. For angular momentum, we pick a specific point in space as our point of reference for angular momentum. Now, here's where I tend to say a bunch of things that don't matter, that you tend to not have to write down because they never come up again, but you might find them confusing. I want to say this. You can pick any point you want. You just need a common point for all of the objects you're observing. You can pick any point you want, but it needs to be a common point for all the objects you're observing. Now that's the truth, that's the way the thing works. But since these are notes and I want you to be successful, they're going to tell you what the point is. It's one of two places. You either pick the obvious pivot point. You pick the obvious pivot point. It will be obvious. And you'll see the first example we're going to do, there's an obvious pivot point. So you either pick the obvious pivot point or it's the center of mass. It's one or the other. So although you can pick any place in the universe, it's one of those two places. So let me tell you specifically what angular momentum is. I have picked a point of reference. You guys see the point of reference here, that little X? And I'm going to move that little X to the side just a little bit so that we have a little more room for me to draw this. So this is going to be our point of reference. This is where the two disks were going to stick together. Everybody okay with that? Angular momentum is a lowercase script L. I just write it like that. And it's script so that you don't think it's a 1. And it's written like this. It's just R cross P, where P is momentum. A reminder, P is momentum. So to understand what I'm saying when I say R cross P, the first thing I'm going to do is I'm going to draw in R so we know where R is. R is the arrow drawn from our point of reference to the center of our object. That is R. P is going to be mass times velocity. So if you want, we could write this as R cross mv. It is a vector. It has direction. But remember, this is a right-hand rule issue. This is rotating. This has a rotational direction. Now, I'm going to do this because I didn't do it in third period, and I should have. You should figure out how to use the right-hand rule for this. It's not obvious. So fire up your right-hand rule, but you may not want to use the board. You may want to use your piece of paper in front of you. Because if you don't remember how the right-hand rule works for the cross product, your pointer finger is the first vector, and your middle finger is the second vector, and your thumb is the result. So, pointer finger along the green arrow, but V is going back that way. So I'm going to flip my hand over so I can easily move my finger to indicate that it's back that way. My thumb points into the board. I know, that's weird and perhaps a little uncomfortable. But remember, it's a rotational vector. Now, if you don't understand that, I want you to use your imagination. Okay, here we go. Ready? Watch this green arrow. If this object were just to go right on by, do you realize that that green line would just go like that as it passes on by? That it's just going to turn in that direction? Right? It's a rotational vector. It's got to be into the board. It's still about rotation. Does that make sense, you guys? Follow that okay? I know it's not obvious and it's so weird to do the right-hand thing for this object that's going in a straight line. It's about to get weirder, so is that okay so far? So here's what I mean when I say it's about to get weirder. Look at that picture. There's an angle right here. We'll call it phi. Because the cross product, when we look at just the magnitude, is R mv sine phi. Phi is that angle between R and the velocity. Yes, sir?
That was my question.
Yeah, phi is this angle. It's hard to draw it in there because it's really small. I'm going to draw a much better picture of this in just a minute. I'm just trying to get us started. Now, follow this argument for a minute, because this is what I need you to. This is what I really need you to see. In a few moments, the object's going to move to here, right? It's going in a straight line. It has a constant momentum. So in a few moments, the value for R is going to change. It's going to become this. The velocity is going to stay the same. But you have to agree that this angle, phi, has now also changed. In fact, I'm going to call that phi 2 and this R2. So the question is the object's angular momentum changing? You notice that R is getting shorter, right? It's going to get shorter for a while until it gets right up next to that point, and then it's going to get bigger for a while as it goes on. So if I gave these numbers here, I'd say R1 mv sine phi 1. Right, that's here at state 1. And then without anything happening to it, traveling at a constant velocity, suddenly it's R2 mv sine phi 2. Nothing happened? No outside force? Don't these have to be equal? Because if they weren't equal, the momentum would have changed, which meant it would have been an outside torque. Now, I can prove that these things are equal. It's just a little bit of geometry, and it's worth proving that they're equal. And the reason I need to prove that they're equal is because how I'm going to prove that they're equal is going to give you something you need to solve these problems. Okay? So we're going to prove that they're equal. To prove that they're equal here, that we have to have this point of reference, I'm going to just draw that again without drawing the pucks. But I'm going to do one little thing different. I'm going to put a red line here to represent the it represents the line that the pucks were traveling on. Does that make sense? So like, I'm kind of zooming in, but let's imagine that the puck was traveling along this line. Is that okay? I'm just going to remove the puck because it's in the way. And let's remember that the puck was here at one point and then here at another point, and this was the closest approach. So R1 was not that. This is R1. And with that, this is R2. Okay. I'm going to draw in a new R to help us. And I'm going to imagine that eventually the puck makes it right to there. Because that will happen, right? Eventually the puck will make it there. Now I'm going to give this one, I could call this R3. But instead I'm going to call it R perpendicular, because that's the point that is perpendicular. Right? It's perpendicular to the point in question. It's like straight up and down. Now at the same time, this is phi 1. And this is phi 2. Bless you. Okay, so everybody agree this is okay so far? Let's take a look at a clear triangle that I see here. I see that triangle. Do you see that triangle? Do you see a relationship between R1, phi, and R perpendicular? Like, if this is the right angle, isn't this the opposite side and R1 is the hypotenuse? So that would suggest that R1 sine phi 1 equals R perpendicular. Does everybody see that okay? Let's go to the other triangle I see here. I see this triangle. Do you guys see that triangle? Do you see that there is a relationship between R2, phi 2, and R perpendicular? And do you also see that it is R2 sine phi 2? So if two things are equal to the same value, they are equal to each other. Does that make sense? So first, I want to show you, tell you that means that R cross P does indeed stay constant if the object's velocity stays constant. We have proved that. But also, we've proved something else. And this is critical, the most important thing I'm going to say, because this is what you will actually do in your problems. That these, although equal R mv sine some angle, they also equal R perpendicular mv. This R perpendicular is known as the point of closest approach. The point of closest approach. We will never use this stuff. Every one of our problems is going to involve a collision where the object will get close. So I can count the number of times this has been on the exam on one hand and only use 2 fingers. I can count the number of times this is on the exam, or has been on the exam, and I don't have enough fingers and toes for it. So do you know which one of these is going to be more valuable to know? And that's what I want to do today. I want to show you how we use this. Okay? I do have all my fingers and all my toes, just so in case you're wondering. I don't have any extras, and I have yet to lose any, but the year is still young. Who knows? Here's way back example we're going to use. I want to talk to you about how, I don't want to do the puck example. The puck example is okay, but it's more complicated than is necessary. This example we're going to do right now is pretty common. And when I say common, I mean that I can probably just reach into a bag full of AP exams and pull this one out. All right, so as an example question goes, I'm going to do this. I'm going to say we have a meter stick, okay, just a rod or something, and I'm going to hang it so that it just barely grazes the floor. So the red line is the floor, and I'm hanging it perpendicular. I'm going to say it's attached here at the very top so that it can swing back and forth about that pivot point right there. Is that okay? So I'm also going to have a little block down here that has a velocity v and mass m. It is going to strike and stick to the rod, and therefore the block and rod are going to swing upwards. So there's going to be a situation in just a minute where, let me just make this a little easier to draw for me. Where those two will stick together and see if I can get this to be my friend. There we go. Yeah, it'll do something like that. Can everybody imagine that? This is a very typical angular momentum collision. It's got all the qualities I would expect. And I see future qualities too. I mean, clearly I have a point mass that's going to strike something, and then they are going to have some rotation after the collision. And then after the collision, that rotation is going to involve gravity and stuff like that, about how high it swings upwards. Do you guys see that kind of thing happening in the future? There's clearly a collision. In addition to that, I see a future problem in a way we can do this, like different types of things that can be asked. Things like how long does it take to swing back and forth? That's simple harmonic motion. We're turning this into a pendulum. What's the maximum height attained by the block? What's the maximum degree attained by the system? I can run this problem in reverse. In reverse, this is a golf club hitting a ball, right? A similar kind of question where the object is rotating first, then has a strike, and the object that it strikes has linear momentum after the collision. This is pretty typical. And so let's put some numbers to this just to make it easy. We'll say that the rod is length L and mass 5m. That way we have something from which to work. What I'd like to show you is how we would figure out how fast the block and rod are rotating after the collision. Because I think you can probably see that that would determine how much energy it has after the collision, and we could do an energy problem after this. So we're only going to handle the collision part. And what I mean by that is we're going to consider finding out what happens right after the collision. We're going to take this thing here. See if I can just do this at once without having to redraw it all. There we go. Okay. There we go. So I want to find out the angular speed of the system right after the collision. The middle ground. Because afterwards, the whole thing swings upwards. Let me remind you, I used to say these words quite frequently when we were doing collisions a month ago. A collision is the moment before and the moment after contact. Do you remember me saying that? So right now, when we look at this, do you realize why I told you that we're always going to use R perpendicular? And if you don't realize it, let me just be clear. We don't know where this object started. We don't know what the original R is or the original angle. They'll never tell us that because we don't care. Our problem actually doesn't begin until this little block is just about to strike the rod. That's where our problem begins, is the moment before it strikes the rod. So when I'm trying to find the angular momentum of the system, I notice that the angular momentum of the system isn't going to be R mv sine some angle. I'm going to advance the object till just before the collision and use R perpendicular mv. They're not going to give us R. Just like in this problem, you're going to have to figure it out from the known information in the problem. Meaning, you notice that we know what R is, don't we? We know R perpendicular. If you're watching closely, you realize that R perpendicular here is probably L. It strikes at the bottom of the rod. That's got to be what R perpendicular is. And that is going to be our angular momentum. So although they'll start the object far away, and they may even give information about where it starts. That's all distractor, because the actual thing that matters is where it strikes the object. That's what matters, that R perpendicular value. Now, doing that part isn't terrible. However, how you do the next part, you have options. I'm going to show you the way I like to do it, but there are other options that we could talk about. This is the way I like it. I see this as a new object that's been made during the collision. It's a rod, which has one moment of inertia, and it's a box, which is a point mass attached to the bottom. I see that object as having two combined moments of inertia. Now, I didn't say this a minute ago because I got myself distracted, so let me back up. I never said out loud what my point of reference is, and I made clear. So is it obvious to you that I was choosing that as our point of reference? And I chose it because I knew the system was going to pivot about that point later in the problem. I didn't make that clear, and I probably should have, and so for that, I am sorry. That's where I got the L from, because I chose that as my pivot point. So now that I know that, I think we can do the rest of the problem pretty easily, because the moment of inertia times omega is going to be the final angular momentum of the system. It's a rotational angular momentum, sure. It's not a point mass angular momentum. But remember, angular momentum is conserved, so these things will have to be equal. So I'm going to do the obvious thing. I'm going to find the moment of inertia. First, 1/3 times 5m times L squared. That is the moment of inertia of the rod, 1/3 mL squared. But I have to put 5m in for the mass. Then the box is a point mass at the bottom. That's just mL squared. That is the moment of inertia of the system. That has to equal omega. Now, the rest of this is just alphabet soup, right? You guys find one letter or the other. I'm not too worried about it. I can write this as LMV, and this side's going to be 5/3 plus 3/3, 8/3, mL squared times omega. I have every bit of confidence that you guys can do algebra. Maybe not the first time, and maybe not the second time, and sometimes maybe not the third time, but by the fourth time, you tend to do the algebra okay. but you're just going to solve this for omega. You guys see that, right? There is some things here worth looking at. You cancel the masses out. That's only because I made the masses proportional to each other. I can cancel out one of the L's, but not both L's. When I solve for omega, in this case, I get 3v over 8L. Ignore the 3/8. That's a product of it being a rod. That's where the 1/3 came in. But look, V over L. It makes sense that the speed that it swings upwards is proportional to how fast the block was going. Doesn't that make sense? I think that makes great sense. Another interesting thing I see here is that how long it is makes a difference too. If it's really, really long, it doesn't swing very fast. That seems reasonable to me, right? If it was really short, it'd probably spin around. But if it's really, really long, it probably wouldn't move that fast. These all make sense, like a little bit of intuition, I guess. Now, I'm near the end of the period. In the other class, I sent them off with an assignment, with a problem. And I said, remember the merry-go-round from yesterday. I said, what if one kid shows up today by himself, no friends, and he decides he wants to play on the merry-go-round, so he runs and jumps onto the merry-go-round. If there's no external torque on the system, and he's taking his 60 kilograms, running at 3 meters per second, how fast will the merry-go-round be going when he jumps on it and it begins to rotate? This is a good practice question. And because I know they're going to ring the chime here in a minute, I'm going to leave you with that. I've written a group of questions. I'm going to post those. I will send out an announcement with this numerical answer.